This is Physics 104A at Porterville College, Chapter 1 Homework Solutions, starting with number 10. Number 10 says the power output of a typical large power plant is 1,000 megawatts. Express the result in watts, kilowatts, and gigawatts. Okay, so it's a unit conversion. We start with 1,000 megawatts. For part A, what I did here was recognize that mega means 10 to the 6th. So essentially, you can replace the word mega with times 10 to the 6th. So the 1,000 is 10 to the 3rd times, and here's your mega, 10 to the 6th watts, which leaves you with 10 to the 9th watts. For part B and C, I followed the convention of how we do unit conversions. We start with, in part A, we got 10 to the 9th watts, and now we're going to do a conversion to kilowatts. So we recognize that 1 kilowatt is 10 to the 3rd watts. So we take 10 to the 9th watts over 1, multiply it by the conversion, 1 kilowatt over 10 to the 3rd watts. We put the watts on the bottom and the kilowatts up top so that the watts here and the watts here will divide out, leaving us with the units of kilowatts, so 10 to the 6th kilowatts. In part C, we do the same thing. We start with 10 to the 9th watts that we got in part A, and then we want to convert it to gigawatts. So we recognize that giga means 10 to the 9th. So 1 gigawatt over 10 to the 9th watts. When we multiply watts in the numerator, watts in the denominator, they divide out, and we're left with 10 to the 9th over 10 to the 9th gigawatts, or 1 gigawatt. For number 11, the diameter of a hydrogen atom is about 0.1 nanometer. Diameter of a proton is about 1 femtometer. How many times bigger than a proton is a hydrogen atom? So we can set up this problem by saying this. The diameter of an atom is K times the diameter of a proton. So K is the answer we're looking for. How many times bigger than a proton is an atom? So we want to solve for K. Algebraically then, K is diameter of an atom divided by diameter of a proton. Plug in the numbers, equals 0.1 nanometers over 1 femtometer. Now we need to get this as a, we need to make these units cancel out. So we can start by just having 0.1 nanometers over 1 femtometer. Recognize that nano means 10 to the negative 9. Femto means 10 to the negative 15. So we're going to replace, when we see nano, replace it with 10 to the negative 9. When we see femto, replace it with 10 to the negative 15. So 0.1 nanometers will become 0.1 times 10 to the negative 9 meters. 1 femtometer will become 1, and instead of femto, we say times 10 to the negative 15 meters. When you do the math, the units of meters will divide out, and we're left with 10 to the 5th, which answers the question up here. The diameter of an atom is 10 to the 5th times the diameter of a proton. Number 20. We're comparing an estimate that a year is about pi times 10 to the 7 seconds with the true number of seconds in a year, and seeing what is the percent error. And this is something that will come up often in our labs, and we'll talk about that during the first lab when we look at error estimates. But this is the equation you should know, and that you'll be using in many of your labs throughout the semester. That percent error of anything is of any kind of estimate for any value is the difference between the true value and the estimate divided by the true value. Now in the numerator, the difference between true value and estimate, I put that in absolute value form because we want this will always come out to be positive. So whether true is larger than the estimate or true is smaller than the estimate, that'll affect whether it's positive or negative. We don't care if it's positive or negative. We just want to make it positive. We just want the positive difference. So we take the absolute value. So it's the difference of the two divided by the true value. Now let's see what values we're talking about here. The estimate in this case is pi times 10 to the 7th seconds in a year. The true number of seconds in a year, you can compute that by doing 3,600 seconds per hour times 24 hours per day times 365 days per year, and you get 31,536,000 seconds per year, which is very close to pi times 10 to the 7th. But let's see what the percent error is. You plug in those values, so the true value, we just calculated it, minus pi times 10 to the 7th divided by the true value, and we get a percent error. You should get 0.003808. That's the percent error. That's actually in decimal form. If you want it as a percentage, you multiply by 100, so it comes out to be 0.38% error. Number 21 asks how many cubic centimeters are in a cubic meter. So simple unit conversion. We start with 1 cubic meter. Since it's not as a ratio, just put it over 1. We're going to multiply by a fraction that's equal to 1. In this case, 1 centimeter over, and remember centa means 10 to the negative 2, so 10 to the negative 2 meters. Remember, whenever you do a unit conversion, numerator and denominator, they have to be equal to each other, because this whole fraction needs to be equal to 1. And the other thing is, the units that you want to go away, if they started out on top, you need to put them on bottom. So meters and meters will divide out. Now there's one more thing we need to do. Recognize, in the original information, it's not just 1 meter, it's 1 cubic meter. Down here is only 1 power of meters. So we need to cube that. We're going to cube this entire fraction, which means that this becomes centimeters cubed. This becomes meters cubed, which will divide out with this meters cubed. But also important is that this 10 to the negative 2 in the denominator, it gets cubed, so it becomes 10 to the negative 6 in the denominator, which becomes 10 to the 6th cubic centimeters. Number 23. You have 350 square feet covering a gallon. I'm sorry, being covered by a gallon. What is its coverage in meters squared per liter? Okay, so a unit conversion. We want to go from feet squared in gallons to meters squared in liters. One decision you have to make in the beginning. You might at first set this up as 1 gallon over 350 square feet, because that's the order that the problem gives it. It mentions gallons, then 350 square feet. And while that's not wrong, let me give you a hint for starting this. Recognize that you want to end up with meters squared per liter, because that's what the problem's asking for. So if you want to end up with area per volume, it'd be easier to just start with area per volume. If you don't do this, the way I've done it here, and you start with gallons over square feet, you'll get some answer, and then you'll just take the reciprocal of it to get feet squared over gallons. But let's start it this way. Feet squared per gallon, 350 feet squared per gallon. You have to do a unit conversion. We want to turn feet into meters, so that's something you can look up in the front flap of your book. The conversion is 1 foot is 0.3048 meters. Recognize that since that's feet squared, we have to square all of this, so including the 0.3048, that'll get squared, and your feet squared will go away. You're left with meters squared per gallon. Now, we need to convert gallons to liters. You can look that up on the internet, do a Google search. Personally, I looked it up on a carton of milk that's in my refrigerator at home. I found a gallon carton of milk, and it says right on it, 1 gallon, 3.78 liters. So that's where I got this conversion. 1 gallon is 3.78 liters. So the gallons will divide out, and what you're left with is 8.60 meters squared per liter. The last question comes with a really neat solving technique that I want to show you. It asks, how many Earths would fit inside the Sun? So we're looking at what is the ratio of the volume of the Sun to the volume of the Earth. So the answer will be the ratio volume of Sun divided by volume of the Earth. Now these are all roughly spherical objects, so we'll use, we don't have given to us in the book the volume of the Sun or the volume of the Earth, but we do have given in the back flap of the book the radius of each of those, and we can relate volume to radius. So we need the formula for volume. So volume of the Sun becomes 4/3 pi radius of the Sun cubed. Volume of the Earth becomes 4/3 pi radius of the Earth cubed. Rather than plugging in the numbers right now and solving for those volumes, here's something really neat you can do. The 4/3 and the pi, they divide out from the numerator and the denominator. And what you're left with is just simply a ratio of the cubes of the radii. And this is a really neat technique because in case maybe you don't remember that its volume of a sphere is 4/3 pi r cubed. You need to remember the r cubed part, but the 4/3 and the pi don't make a difference. They divide out. The ratio of the volumes is the ratio of the cubes of the radii. So here we have in its simplest form the radius of the Sun divided by the radius of the Earth cubed. You can find in the back flap of the book those different values. This thing in parentheses comes out to about 109. The Sun's radius is about 109 times that of the Earth. Cube that, and you get about 1.3 million. And that's the end of the Chapter 1 homework.